Okay, big ups to everyone watching. Thank you very much for being part of the physics classroom. This is another episode of the BJ's physics classroom, which is going to deal with thermal expansion and contraction in liquids and gas. In the previous episode, we looked at thermal expansion and contraction in solids. And we said that when we meet again, we'll talk about thermal expansion and contraction in liquids. So stick and stay with me and let me take you through it. After that, I'll post some questions on the Facebook page and I expect that you answer the questions and then send it to me so that I'll look at it and see whether what I'm doing here is making I'm making progress in what I'm doing. Thank you very much. So let's begin. But before I do that, if you haven't subscribed to my YouTube channel, please make sure you do that. The channel is bjonline.com. Subscribe to the channel, turn on the notification button whilst you subscribe so that anytime I post a video, you'll be able to get it. And then things will go well for us. Good. Thank you. So, when we talk about thermal expansion and contraction in liquids, liquids generally expand when they are heated and contract when they are cooled. Most liquids generally behave like that. So when we sketch a graph of volume versus temperature for most liquids, the graph is like this. Some of them expand exponentially, yes. Example is alcohol. But water behaves differently. So the behavior of water or the expansion and contraction of water is referred to as the anomalous behavior of water. So anytime we say the anomalous behavior of water, we're talking about thermal expansion and contraction of water. Good. How does water behave? What happens is, when we sketch a graph of volume versus temperature in degrees Celsius or in Kelvin, volume in meters cube. At 0 degrees Celsius, water has a certain volume. Water has a certain volume at 0 degrees Celsius. So while the temperature increases, the volume of the water decreases until the temperature is 4 degrees Celsius. Now, after 4 degrees Celsius, when the temperature of water begins to increase, then the water begins to expand. This behavior of water is what we refer to as the anomalous behavior of water. All matter, if it were any other matter, it was supposed to continue to contract like that, but water after 4 degrees Celsius begins to expand. What that means is that because density is inversely proportional to volume, then as the volume of water decreases, the density of water will be increasing until at 4 degrees Celsius, when the volume of water then begins to increase with increase in temperature, the density of water then decreases. This behavior of water is what we refer to as the anomalous behavior of water. And, God in His own infinite wisdom has reasons why He made water to behave like that. Because if water is not like that, probably aquatic organisms wouldn't get a place to live. Especially when you go to the polar regions where sometimes the temperature can become very low as minus 10 degrees Celsius. So what happens is that with these aquatic organisms surviving at the polar regions, when the temperature of water begins to decrease, the volume of water decreases. Until the temperature is 4 degrees Celsius. After 4 degrees Celsius, the water is, after 4 degrees Celsius, is approaching 0 degrees Celsius, so it's getting to freeze. At this point, the density is maximum. Then as the volume increases, the density begins to decrease, and then the cold water then begins to come up. stay on top of the sea level, the ocean, while the hot water goes down. Good. So at 0 degrees Celsius, the water which is at the top then begin to freeze because its density has reduced, so it comes on top. Then as it gets frozen, its density reduces further. As it gets frozen to very low temperatures, its density reduces further, like that. So as the density reduces further like that, the ice now continue to stay on top of it, on top of the sea, while the down is still water. Why? Because ice is a bad conductor of heat. Because ice is a bad conductor of heat, when the ice forms on top of the sea or the ocean, it serves a barrier between the environment and the beneath of the ice. So now there is no temperature exchange between the environment and the water beneath the ice. So the water beneath the ice still stays as water for aquatic organisms to live in, whilst the top of the water is frozen. So you see it on TV that people use it for sports and stuff like that. Good. So that is one of the applications of the anomalous behavior of water. And in other words, another application of thermal expansion and contraction in liquids. Good. So let's look at types of thermal expansion and contraction in liquids. So types. We have two types. Two types of thermal expansion and contraction in liquids. We have one, apparent expansion in liquid. Now, when we say apparent expansion in liquid, we are talking about the expansion of a liquid without taking into consideration the expansion of the containing vessel. What do we mean by this? You cannot heat a liquid without putting it in a container. So once you heat a liquid, the container heats first. So the container begins to expand. Then the liquid also expands or contracts. So what happens is that when we try to look at the expansion of the liquid without taking into consideration the expansion of the container, then we talk about the apparent expansion of the liquid. However, when we consider the expansion of a liquid, whilst taking into consideration the expansion of the containing vessel, we call it the real expansion of liquid. Real expansion of liquid. So we have two types of thermal expansion: apparent expansion and real expansion of a liquid. Just like we looked at under properties of thermal expansion and contraction in solids, I told you that solids have a special property that determines the expansivity, that distinguishes its expansivity from another material. And that property, we call it the linear expansivity. Under liquids, we call it the real expansivity. The real expansivity of the liquid. So let the real expansivity of a liquid be gamma. The real expansivity of a liquid be gamma R. Gamma R. You remember that expansion of a liquid is the expansion of the volume of the liquid. And then when we dealt with thermal expansion and contraction in solids, we represented the cubic expansivity by gamma. So because we are still dealing with volume, let's call the expansivity, the real expansivity of a liquid, as gamma R. Then the apparent expansivity of a liquid, let's call it gamma A. Gamma A. So therefore, the real expansivity of a liquid is equal to the apparent expansivity of the liquid, plus the expansion of the containing vessel. This is coefficient of volume expansion. This is apparent expansivity of the liquid, and this is the real expansivity of the liquid. So all that we have to do is to determine the apparent expansivity of a liquid. And then we add it to this, that will give us the real expansivity of the liquid. So what is apparent expansivity? The apparent expansivity of a liquid is defined as the mass of liquid expelled per the mass of liquid left times change in temperature. The mass of liquid expelled per the mass of liquid left in the container times change in temperature. You know, what we do is that here we describe a simple experiment, but for the sake of time, I wouldn't go through the experiment. In that experiment, we fill a container, which is specific gravity bottle, with liquid. Then we heat the container, the liquid in the specific gravity bottle. Once we heat it, the liquid will overflow. We allow the liquid left inside the container to cool. Then we find the mass of the liquid that is expelled. We find the mass of the liquid that is left inside. Then we find the change in temperature, that is the initial temperature before we started heating, and the final temperature after we heated. And then we use that to find the apparent expansivity. But we put that here and add it to the expansion of the container. That will give us the real expansivity of liquid. So basically, this is what we need to know about thermal expansion and contraction in liquids. Applications of thermal expansion and contraction in liquid. I've already told you that to help aquatic organisms to survive, the anomalous behavior of water does it. And that is one of the applications of thermal expansion and contraction in liquids. It helps aquatic organisms to survive. 2, because of the anomalous behavior of water, bottled drinks are not filled to the brim. So there is always a space allowed at the top to allow room for expansion, because these bottled drinks, as example is Coke, are made of some large percentage of water. And this is going to be put in the fridge so that it will chill for people to drink it, because people like it chilled. So for that matter, when the temperature goes below 4 degrees Celsius and the water then begins to expand, if a gap is not left at the top and the water inside these bottled drinks expand beyond its capacity inside the bottle will then crack. So to prevent the bottles from cracking and breaking, gaps are always left at the top of these bottled drinks to allow room for expansion. So these and many more are some of the examples of thermal expansion and contraction in liquids. Any physics book that you have around with you, read it, and then you will see some of these applications. Now let's look at thermal expansion and contraction in gases. Thermal expansion and contraction in gas. To deal with this, gases also generally expand when they are heated and contract when they are cooled. Unlike water, gases behave linearly with change in temperature. Now, the discussion of thermal expansion and contraction in liquid in our syllabus is centered on the thermodynamic aspect of gas. In other words, it is centered on the application of the kinetic theory of gas, kinetic theory of matter to the gases. So we need to look at the assumptions of the kinetic theory of gas. Now, basically, in simple terms, the kinetic theory of gas speaks about the fact that gas is made up of large number of molecules that are in constant random motion, colliding with themselves and with the walls of the containing vessel. And when temperature is supplied to this gas, the gas acquires kinetic energy and then begins to move. That is basically what the kinetic theory of gas is all about. Now, in dealing with gases, scientists modeled a gas. So that gives us two types of gases. They modeled a gas and they dealt with it. Then later they compared it with the reality or the real gas. So we have two types of gases. So we look at types of gas. Types of gas. We have 1, real gas, and 2, ideal gas. Ideal gas. The modeled gas is the ideal gas. It's a gas that doesn't really exist, but real gases can be made to behave like the ideal gas, yes. And the real gas, that is the actual gas that exists. Let me say that gases in the universe are real gases, you understand? Good. So let's first deal with the ideal gas, because the assumptions of the kinetic theory of gas were made for the ideal gas. So we say an ideal gas is a gas that obeys the kinetic theory of gas and the gas laws. That is how we define the ideal gas. It is a gas that obeys the kinetic theory of gas and the gas laws. And the real gas is a gas that does not obey the kinetic theory of gas and the gas laws. So what is the kinetic theory of gas? Or the assumptions of the kinetic theory of gas? 1. We say gases are in constant random motion, colliding with themselves and with the walls of the containing vessel. A gas is made up of a large number of molecules. The collision between the walls of the container and the molecules exert pressure on the gas. The force of attraction between the molecules themselves is negligible. The volume occupied by the gas is negligible. And the only energy associated with the gas is kinetic energy. And this kinetic energy is directly proportional to the absolute temperature. Basically, these are the assumptions of the kinetic theory of gas. You know, the scientist has to assume that this is the behavior of the gas so that they can then put up some explanations to it. So these assumptions are obeyed by the ideal gas. But we said that an ideal gas is a gas that obeys the gas laws and the assumptions of the kinetic theory of gas. So let us look at the gas laws. The gas laws, before I'll come back to the ideal gas and the real gas again. So, the gas laws. The gas laws. Basically, we are going to look at 3 of them. So 1, we have the Charles law. Charles law. The Charles law states that the volume of a fixed mass of gas at constant pressure is directly proportional to the temperature, the absolute temperature. Remember that in dealing with gases and with the gas laws and thermal expansion and contraction in gases, the temperature we use is absolute temperature, which is temperature measured in Kelvin. If you use temperature in degrees Celsius, your answer will be wrong. Take note of that. Temperature measured in Kelvin. So according to the Charles law, the volume of a fixed mass of gas is proportional to the absolute temperature at constant pressure. So this gas law, in thermodynamics, we call it isobaric process. Isobaric process. Iso means constant. Baric or bar has got something to do with pressure. So a constant pressure thermodynamic process. Process whereby volume is proportional to temperature at constant pressure. All right? Good. That is the Charles law. So when we rearrange this, or we introduce a constant and an equal sign, we are going to get V is equal to a certain constant times T. So let's this be for one particular gas process, and then for another gas process, V2 is equal to K times T2. When we divide this equation 1 by equation 2, then K will cancel K, and finally we get V1 over V2 is equal to T1 over T2. This is finally what we get from the Charles law. Take note of this equation very well. The most important things: 1, the definition of the Charles law. You must be able to state the law, not the definition. You should be able to state the law, the Charles law. And you should be able to write this formula so that you can use it for calculation. Now, a graph, when we look at this critically, a graph of volume versus temperature. A graph of volume versus temperature. For temperature in Kelvin and volume in meters cube, the graph is like this. It starts from the origin and it's linear. But For graph of volume versus temperature in degrees Celsius, graph of volume versus temperature in degrees Celsius, volume in meters cube, the graph is like this. Why? Because 0 Kelvin corresponds to minus 273 degrees Celsius. So the graph will make contact with the temperature at the temperature axis at minus 273 degrees Celsius point. I hope that is clear. So you must know the distinction between this graph and this graph, this formula, and then how to state the law for the Charles law. Charles law, isobaric process, constant pressure process. Let's look at law number 2, the second law. Well, the laws don't come in any special order. Any one of them can be 1, 2, or 3. So law number 2. So let me write the gas laws. The gas laws. Number 2. We have the Boyle's law. Boyle's law. The Boyle's law is also referred to as isothermal process. That is a thermodynamic process in which temperature is kept constant. Thermal stands for temperature, in which temperature is kept constant. So what that means is that in the Boyle's law, it states that the pressure of a fixed mass of gas is inversely proportional to the volume of the gas. The pressure of a fixed mass of gas is inversely proportional to the volume of the gas. So from this, when we rearrange just like we did for the Charles law, we are going to get P1 V1 is equal to P2 V2. So what I want you to do for me is that remove this proportionality sign, introduce a constant, make that K the subject, do it for 2 processes, for the first pressure P1 P2, for the first pressure P1 V1, and then the second pressure P2 V2, and you'll see that you finally arrive at this formula. This formula too is very important. At constant temperature, the pressure of a fixed mass of gas is inversely proportional to the volume, so that we get P1 V1 is equal to P2 V2. Now, when we sketch a graph of pressure versus volume, the graph behaves like this. So, graph of pressure versus volume, the graph behaves like this. If we look at the third law, we call it the pressure law. We call it the pressure law. And the pressure law states that the pressure of a fixed mass of gas at constant volume is proportional to absolute temperature. The pressure of a fixed mass of gas at constant volume is proportional to absolute temperature. So in thermodynamic principles, the pressure law is referred to as isochoric process or isovolumetric process. So either isochoric or isovolumetric process, that is what the pressure law is referred to. That is a thermodynamic process where volume is kept constant, isovolumetric or isochoric process. So just like we did for the Charles law and the pressure law, when we manipulate this, we introduce a constant and then we do it for 2 processes. We finally get P1 over T1 is equal to P2 over T2. P1 over T1 is equal to P2 over T2. All right? Good. So now we have 3 formulas. P1 V1 is equal to P2 V2. P1 over T1 is equal to P2 over T2. And then V1 over T1 is equal to V2 over T2. All right? You can rewrite it as V1 over V2, then T1 over T2, or you can write it like this. Take note of these formulas very well. Remember, I have told you that temperature is absolute temperature. So temperature measured in degrees Celsius. Sorry, Kelvin, not degrees Celsius. So in the same vein, when we sketch the graph of pressure versus temperature, then the graph will give me something like this. For temperature in Kelvin, pressure in Pascal. But for temperature in degrees Celsius, okay, let me clean this one from here. Maybe it won't appear on the camera. Let me bring it here. Pressure proportional to temperature. So for pressure in Pascal versus temperature in degrees Celsius, the graph behaves like this, where this is 0 degrees Celsius and this point is minus 273 degrees Celsius. So take note of these two graphs so that in case it is sketched for you in objectives to choose between, you wouldn't fumble or you will not have problems. Good. So these are the gas laws that we are supposed to deal with. The pressure law, the Bohr's law, and the Charles law. These are the laws that we say that the ideal gas obey. Then there is another law that we refer to as the ideal gas law. The ideal gas law. That one combines the three laws. So the combination of all the three laws, we call it the ideal gas law. And the ideal gas law gives us P1, V1, all over T1 is equal to P2, V2, all over T2. This is another equation that you may be required to use. This equation comes from the ideal gas law, which is obtained from the ideal gas equation. What is the ideal gas equation? The ideal gas equation. The ideal gas equation is given by PV is equal to nRT for n number of moles, where P is the pressure of the gas, V is the volume of the gas, R is the rate constant of gases, and T is absolute temperature. So, this is constant. If we make this a constant, that is going to give us nR. If we make this the subject, that's going to give us nR is equal to PV all over T. You see, PV all over T. So for two processes, to give us P1 V1 over T1 is equal to P2 V2 over T2. That's what gives us this. This is what we call the ideal gas equation. For n moles, for 1 mole, PV is equal to RT. For 1 mole, of a gas. For n moles of a gas, the formula is given as this. Then we talk about the real gas. Now, we have said that a real gas is a gas Now, a real gas is a gas that does not obey the gas laws and the kinetic theory of gas. The assumptions of the kinetic theory of gas. A gas that does not obey the gas laws and the assumptions of the kinetic theory of gas. Good. So, what the scientist did was that he modeled the ideal gas, then he made some corrections to the ideal gas in order to arrive at the real gas equation, or in order to arrive at the real gas. So we look at the real gas equation. It is also called the van der Waals equation of state. The real gas equation is also called the van der Waals equation of state. And the real gas equation is given by P plus A squared over A over V squared, P plus A over V squared, all times V minus B is equal to RT for 1 mole. For 1 mole of a gas. For n moles of a gas, P plus N squared A over V squared, all times V minus NB is equal to nRT for n moles of a gas. For n moles of a gas. Take note of these two equations. This equation is what we call the van der Waals equation of state, or the real gas equation. This is the pressure of the pressure of the gas. The term here, we call it the pressure correction. Which pressure correction? In the real gas, in the ideal gas, or in modeling the ideal gas, we made an assumption that the pressure of the gas is only due to collision between the molecules and the containing vessel. That the collision between the molecules themselves is inelastic. Is perfectly elastic. The collision between the molecules themselves is perfectly elastic, and for that matter, the collision between the molecules themselves do not exert pressure on the gas. But actually, that is not what happens. In the real gas, the collision between the molecules themselves exert pressure. So, what the scientists did was that, in order to make correction to the ideal gas to get a real gas, the scientists had to add the pressure exerted by the collision between the molecules of the gas themselves. And that is this term, which is added to the pressure. Remember that the collision between the walls and the container gives us the pressure, plus the collision between the molecules themselves. That will give us the total pressure of the gas inside the container. The minus B, this minus B, we call it the volume correction. Why volume correction? In the assumptions of the kinetic theory of gas, we said that the gas does not occupy volume. The ideal gas does not occupy volume. But in reality, the real gas occupies volume. So this V is the volume of the containing vessel. In other words, the whole volume occupied by the gas. This B is the volume of the gas molecule itself. The volume of the gas molecule itself. Because we said that the volume of the gas molecule is negligible, so we neglected it. That was why it was PV is equal to nRT. nRT. So now, because we are saying in the real gas, the gas occupies volume, we need to take away the volume occupied by the gas from the volume of the container, so that will give us the actual volume that we want, to deal with. So we subtract this term from the volume of the container to give us the actual volume of the gas. So this B term is the volume correction. This A over V squared term is the pressure correction. When we do this correction to the ideal gas equation, we get a real gas. So you realize that this one is what is added to this, and this one is what is added to this to give us this equation. I hope that is clear. Good. So there are two conditions for which a real gas will behave like ideal gas. Two conditions for which a real gas will behave like ideal gas. One, at very low pressure, and two, at very high temperature. Let me explain this. Why is it that at very high temperature, a real gas behaves like ideal gas? The reason is this. At very high temperature, the molecules of the gas gain kinetic energy. So the kinetic energy of the gas increases. Remember, in real gases, there is both potential energy and kinetic energy. The potential energy comes about as a result of the interaction between the molecules themselves, the force of attraction between the molecules. That brings about potential energy in the real gas. The kinetic energy is the gas molecules in motion, constant random motion. In the real gas, there is potential energy, there is kinetic energy. So when temperature is supplied at very high temperature, the gas gain more kinetic energy. But we say energy is neither created nor destroyed. So what that means is that whilst the kinetic energy of the gas molecules is increasing, the potential energy of the gas molecules is decreasing. It's decreasing because the molecules are spending less time on their collision, on colliding with themselves. So the increase in kinetic energy results in more frequent collision between the molecules themselves, and for that matter, the decrease in potential energy, an increase in kinetic energy. So it gets to a point where the potential energy becomes zero. The only energy now associated with the gas is the kinetic energy at that very high temperature. And so the gas then behaves like ideal. Because we said that the ideal gas, the only energy of the gas is kinetic. You understand that? The only energy of the gas is kinetic. So when temperature increases, the intermolecular force of attraction between the molecules decrease. So you get to a point where the intermolecular force becomes zero. The potential energy becomes zero. The kinetic energy becomes very high, and the gas then behaves like ideal gas. Then at very low pressure, from the Boyle's law, pressure is inversely proportional to volume from the Boyle's law. Pressure is inversely proportional to the volume of the containing vessel. So at very low pressure means very high volume of the containing vessel. In the ideal gas, we assume that the molecules do not occupy volume. The molecules of the gas do not occupy volume. In the real gas, the molecules of the gas occupy volume. So at very low pressure, it means the volume of the container is very high. So when we compare the volume of the molecule with the volume of this high container, the volume of the molecule of the gas becomes insignificant. It becomes negligible. So the gas behaves like ideal. I hope that is clear. These are the two conditions for a real gas to behave like ideal gas. I hope this is clear. Good. So this is basically what we need to know about the thermal expansion and contraction in liquids and in gases. In our next episode, we will deal with heat transfer, where we'll talk about thermal conductivity or thermal conduction, thermal convection, and then thermal radiation. So what I'm going to do is that before I do that video, I will do a video solving questions on some of these things so that you would see how we use these equations I have poured on the board. All right, I'll solve one or two questions on these things. So whilst we wait for that, let us please read the notes in addition to the video we are watching, so that at the end of the day, we'll be able to understand the things very well. Solve a lot of questions. If you solve a question and you can't solve, post it on the Facebook page or bring it to the WhatsApp page. You know what I'm talking about. And then I will look at it for you. So thank you very much for being part of the show. Please subscribe to my YouTube channel, bjonline.com. And thank you. Bye-bye.